Okay, graphs of categorical data. So we have a sample of eye color of 10 newborn babies. 7 had brown eyes, 2 had blue eyes, 1 had hazel eyes. Okay, so this is categorical data. Eye color is a category, it's not a number. So our variable is going to be category. So our scale for the variable, instead of numbers down here, we have categories. And then the vertical scale will be the frequency. And so we have 7 babies with brown eyes, so we make a bar going up to 7. That's for brown eyes. And then blue eyes, we had 2 babies, so we make a bar going up to 2. And then 1 baby with hazel eyes, so we want to make a bar going up to 1. So that's our bar graph. Yeah, one thing to notice about the bar graph is you have equal size spaces between each bar for a bar graph. The reason for that is to emphasize that these are categories and not numbers. Also, it doesn't make much sense to talk about symmetry versus skewness for a bar graph. Usually that's not discussed. And the reason is that the order of these numbers, categories, are arbitrary. If we put, right now it looks like it's skewed right, the longer tail is on the right. If we put brown in the middle, then it's going to look almost symmetric. If we put brown on the right side, it's going to look skewed left. So we don't talk about symmetry versus skewness. It just depends on how the symmetry of the graph, the appearance of symmetry, it just depends on the order that you put them in. If you do put them in order from smallest to largest or largest to smallest, put the bars in order from largest to smallest or smallest to largest, it's called a Pareto chart. That's just a term for that type of bar graph. It's a Pareto chart. And you could put you could put the variable on the vertical scale and the frequency on the horizontal scale. Sometimes that's done. It could be done either way, but usually the variable is on the horizontal scale. And we could have, if we divide the frequencies by 10, we would get relative frequencies. So sometimes you'll see a bar graph with relative frequencies. It's basically the same graph. Brown. We have 7 babies with brown eyes. Total of 10 babies. 7 divided by 10 is 0.7. 2 babies had brown eyes out of 10. 2 out of the 10 babies had brown eyes. 2 divided by 10 is 0.2. 1 of the 10 babies had hazel eyes. 1 divided by 10 is 0.1. So it's the same graph. It's just instead of frequency on the scale here, we have the relative frequency. It goes from 0 to 0.7. So otherwise, it's basically the same graph. And then we could also make these into percents. If you multiply the relative frequency by a percent, 0.7 times 100 is 70%. Percent is parts per 100. So if you multiply by 100, you get 70 parts per 100, or 70%. 0.2 times 100 is 20%. That's 20 parts per 100. 0.1 times 100, 10%. And then, again, the only thing that's different is the way the scale is labeled. Now it's labeled in percent instead of frequency or relative frequency. Otherwise, the graph looks the same. Okay, you could also do a pie chart or circle graph, and you could use frequency or relative frequency or percents. I'll do this for the frequency. So we have 10 babies. I divide the pie into 10 pieces. And there were seven babies had brown eyes, so I get 7 slices of pie for brown. 1, 2, 3, 4, 5, 6, 7. Two babies had blue eyes, so the two slices of pie there for blue. And then one baby had hazel rye. So that's 1 slice of the pie. So there's the pie chart of the circle graph. So if you divide these frequencies by 10, you'll get the relative frequency. So one of the 10 babies had hazel eyes. 1 divided by 10 is 0.1. 2 divided by 10 blue eyes, that's 0.2. 7 divided by 10 or 0.7 brown. And if you multiply these relative frequencies by 100, you'll get the percents. So you can do a pie chart with percents also. For 0.1 times 100 is 10% hazel. 0.1 times 0.2 times 100 is 20% blue. 0.7 times brown is 70% brown. And that concludes this presentation.